In this video, we are going to do an example using the Fundamental Theorem of Calculus Part 1, or FTC Part 1 for short. So this says the graph of y equals f of t is given below, and to let g of x be the definite integral from -2 to x of this function f of t. Okay, so let's recall that this definite integral, what it means is on the interval from -2 to whatever x is. So let's imagine x is somewhere here. We are talking about this, what's called the signed area under the graph. So when part of the graph is below the x-axis like this, that region gets counted as a negative area. And when part of the graph is above the x-axis, that gets counted as a positive area. So g of x would be that area starting when x is -2 up until whatever x is. So I can imagine that if x, were to change and be somewhere over here, well, now I would have a different area. I'd be adding more positive area to the mix. Okay, so what is the question asking? Part A says, find the intervals where g is increasing and decreasing. Okay, so let's do this two ways. First, let's remember that, okay, a function is increasing and decreasing. I can figure that out with the derivative. So my derivative of g, I can get that with the Fundamental Theorem of Calculus Part 1, which says that when you have an area function like this, its derivative is just f of x. It's the function that's here, but replace the variable t with the variable up top to get f of x. Okay, so if we use FTC Part 1, I'm going to say by FTC Part 1, g prime of x equals f of x. So the derivative of the area function is actually just this function that's drawn. So if I'm trying to say when g is increasing, well, that's going to happen when its derivative is positive. So its derivative, we just said, is f of x. I need to know when is that positive. Okay, so when is f of x, this function, positive? Well, that's when its y values are positive. That's this part of the graph, positive y values. So that happens to the right of -1. So from -1 up until 6. Remember, the convention that we're using in our class is when we write these intervals of increasing and decreasing, we're always going to use open intervals, just for simplicity's sake. And similarly, I can say that g is decreasing. G is decreasing when its derivative, which equals f of x by FTC Part 1, when its derivative is negative, so less than 0. So when is this function less than 0? Well, that's over here, when the function's below the x-axis, negative y values. So that happens when I'm on the interval from -3 to -1. Okay, so we got it. When is g increasing? When is it decreasing? The other way I can think about this more conceptually is g represents this area. So when is this area increasing and when is it decreasing? Well, when my function is, to the right of -1, the function's purely above the x-axis. So as my x values get bigger, I would be, adding more and more positive areas. And if that happens, my area is increasing. But if I'm to the left of -1, well, I'm adding more and more negative areas, which would make g decrease. So that's a more conceptual way I can see why I expect this to be the answer. Okay, so let's look at part B, which says find the x values of the local maxima and minima of g, of this area function. So I know now that g is decreasing on this first interval from -3 to -1. So when x is -1, and then it switches to increasing after that. So that means at this point, I'm going to have a local min. Okay, so we will have a local min at x equals -1. And let's give the reason why. Since, and there's two things I need to say. One is that g, let me say, changes from decreasing to increasing. That's one important part of it. That's not enough because sometimes I could have a function that changes from decreasing to increasing, but I have, a discontinuity, and then there is no min point. Like I might have an asymptote or something. So I also need the function to be continuous. It turns out it is. So let me write that down, and then I'll talk about why. And g, the area function, is continuous there. Okay, so why is g, the area function, continuous? Well, I know the derivative of g equals f of x. So the derivative of g exists. That's part of what this says. In other words, g is differentiable. And part of what differentiable tells us is it's automatically continuous. Okay, so that's how I know that g is continuous. All right, so I have a local min at -1. All right, the last part of the question asked me to find the intervals where g is concave up and concave down. Okay, so this involves the second derivative. So g is concave up, I'll just write cu when the second derivative of g, so the second derivative of g, we'll just do the derivative one more time, that would be equal to the first derivative of f. Okay, I would need that to be greater than 0. All right, and then similarly, I can say that g is concave down when the second derivative of g, which is equal to the first derivative of f, when that is less than 0. Okay, so, well, when is the first derivative of f positive? Well, that would happen when f is increasing, and then similarly, f prime is negative when f is decreasing. When f is decreasing. Okay, well, and then f is this graph. F is just straight up this graph. I'm just looking straight up to see when is this function increasing. So it's increasing when, well, there's two intervals when it's increasing. It's increasing here, and then it's again increasing on the second half of this kind of semicircle. All right, so it's increasing from -3 up until 2, union from 4 up until 6, and it's decreasing when on the interval from 2 to 4. And we got it. Got where it's concave up, we got where it's concave down.